So I'm going to tell you a little bit about the history of wall modes, how it died around 2000, how it got resurrected, and now it seems to be everywhere. And it's a fun story, so I hope you'll bear with me as I go through some of these things. This is an example of the difference at the same Rayleigh number, the same Ekman number, between insulating sidewalls and conducting sidewalls. So you can see that at the same conditions, depending on the sidewall, you get very different states, and I'll tell you why. But first, going back to the first experiments that I did, we built an apparatus with Victor Steinberg and my postdoc, Feng Zhang. I'm embarrassed to say that both of us, Victor and I, were low temperature people who were very used to making joints in low temperature apparatus that could resist superfluid helium. When we first turned this on, water went everywhere. But in any case, we designed it to look at the bulk state. And the way that you visualize it, so we set it up to be a very good measurement of heat transport, very accurate measurement of heat transport. For example, our reference thermometer was temperature regulated at the bath temperature. We worked very hard on that. The top was a sapphire window, and we sprayed water on it at different angles in a technique pioneered by Günther Ohlers. And we designed a shadowgraph apparatus, and somebody asked about that earlier. You have a light source which then shines through a collimating lens so that you get parallel light. And as the index of refraction, which is proportional to the temperature, changes, you get a double pass through here. The bottom is a mirror. It comes back up, and you integrate the refractive index over the depth, and this allows you to visualize, at least coarsely, what's going on in the flow. Works really great in thin layers because things are more uniform vertically, but here you're mixing dips. However, we turned this thing on, looking for bulk states, and we saw this. And I remember the first day that we saw this movie, I went, I know what those are, and I went to the earlier papers by Pfotenhauer and Buell and Catton and everything, in which they had hypothesized a state like this that would account for the heat transport that one saw below the bulk onset. And so then we went off on a long journey through understanding wall modes. We always saw retrograde precession, and the nice way to see that is in these space-time plots, in which you see that there's this constant precession rate. Our shadowgraph wasn't all that great in those days. It got better with time. So this is an aspect that I think is one that is interesting to consider, and that is because the wall mode precesses, its heat transport contribution is independent of time. So if you look at the heat transport as a function of time, it's no RMS fluctuations until you get to the bulk state in which Nusselt fluctuations start. And actually, I think that's a useful mechanism, a useful ingredient to look at in both experiments and also in numerical simulations. What is the nature of this time dependence? It's well known that there is a nonlinear instability called the Cooper-Lorentz instability, which happens even at very small, very large Ekman numbers, Ekman of 10 to the minus 1 or so, that lead to very slow time dependence right at onset. So as having been seen before, we were able to identify the onset of the wall mode, and through both the time dependence, which was more accurate, but also through the shadow graph, we were able to identify the bulk state. Okay. Now, when you look at this particular aspect ratio, which is aspect ratio 2, one of the things you see is that it's very hard to distinguish where the bulk state comes in. Turns out that the slope of the wall mode state at these particular conditions is very close to the slope of the bulk state. It's very hard to see the difference between the two. This is more of an editorial comment. When Edgar was talking yesterday, he was very instrumental in us understanding the origins of why you should get a traveling wave in the system. His suggestion that we plotted these things to follow his theory was a bit disingenuous. I had already worked a lot on Hopf bifurcations, and I didn't know the right things to plot before he pointed them out. In any event, the comparison with Rick Goldstein's work showed a very nice comparison between the onset and the finite linear stability calculations. One of the things you notice here is because you're in a finite cylinder, these jumps in here correspond to different mode number changes, because in an azimuthally periodic system, you can only get integer mode numbers. So if you increase, so what we wanted to do was get away from a small number of wall mode periodicities, m equals 4, 5, or 6 for gamma equals 2. So we made a smaller cell. The shadow graph is much nicer in that case. And one of the features that you see here is that if you go to low enough rotation rate, the bulk state comes in directly. If you start increasing the rotation rate, what you see is that if you scale things, epsilon is Rayleigh over Rayleigh onset of the wall modes minus 1, this slope is pretty much independent of the rotation rate until you cross over to the bulk. And in this case, you get this very nice distinction between the wall mode state and the bulk state. Let me just show you the movie. There's lots of interesting dynamics that go on here that I'll explain just very peripherally. But when you add in but you can see that the wall mode in this aspect ratio 10 is very concentrated near the boundary. If you go to the case where the bulk mode has come in, you see this very nice, there's a couple of features of this. First of all, there's this very nice separation. There's this inner part, which looks very bulk-like, without much influence of the wall mode. And the wall mode's happily processing around it, which always led me to the notion that it would be a simple separation between the bulk state and the wall mode. The other thing you can see in that movie is the time dynamics associated with how ostensibly independent vortical contributions kind of couple and uncouple in this kind of rotating way, which is reminiscent of the Cooper's-Lorentz instability, which is a switching instability of roles. And this is the mechanism that leads to this time dependence at onset. If there are any questions, please feel free.
Those were also experiments, right?
Yeah, that was all experiments.
Okay.
Yeah. I always like it when somebody asks the question, is that an experiment or a numerical simulation? It's kind of like, yeah, we did a good job. We did a good job. So here's an example. Here's another feature of this is that here's kind of the width of the wall mode state for different aspect ratios. This is 2, 5, and 10. And one of the things you can see is that this gets a little narrower. It's considerably narrower there with respect to the total radius. And you can also see that the bulk state now is less obvious in the middle than it is here when the aspect ratio gets very large. And roughly speaking, you can figure out that as the aspect ratio goes up, you should get a smaller and smaller contribution from the wall mode because, of course, the total area of the cell, which you're normalizing by, is getting bigger.
So you're going from gamma 2 to gamma 5 there?
This is gamma 2, this is gamma 5, this is gamma 10. And so the dashed line is just 1 over gamma. It's not quite that way, but I think there are good reasons to expect deviations. But in general, it goes down. So, you know, the answer to what you need to do in rotating experiments is to just go to big enough aspect ratio, and then all these problems go away.
Bob, I have a question. In
Yeah.
that slide, so was there like a critical aspect ratio? So for A, for example, it's almost the wall modes and the bulk are coupled, and it's like you can't separate them. Was there like a critical aspect ratio at which you can see?
Hold that question, key question that will ruin everybody's life. Yes.
What's your Ekman number? What length scale is there? Is it the radius or the height in your Ekman number?
The Ekman number is always defined by the height.
The height?
Yeah.
So as you go to larger aspect ratio, like in the actual lab, are you keeping the height the same and just widening the?
No. No, it's complicated by the mirror geometry. You know, in this particular thing we used polished silicon plates, and you know you can only get them so big before it gets too expensive, and so you just narrow the height, which of course lowers the range of Ekman number and Rayleigh number you can get. But you can still find overlapping regions between the different aspect ratio data. So one of the things that's important to point out is that depending on how you do this, you can get a large number of possible integer at large aspect ratio. You can get a very large range of possible states. So from a mode number of 17 up to a mode number of 31, depending on how you manipulate the system. So you jump quickly to a Rayleigh number, you go adiabatically slowly, you go up and change the rotation rate back and forth. And my postdoc, Yuanming Liu, was very clever about figuring out how to access essentially the whole spectrum of 14 different M numbers between 17 and 31. And what you get then is a band. So this is the linear stability boundary, approximated as a quadratic with a certain curvature associated with it. And then it was predicted for these kinds of nonlinear traveling waves that there would be an instability that would allow you, if you came down here at a too high a wave number and you hit this boundary, then it would undergo a transition back into the stable band of states. This is the kind of Busa balloon for this little traveling wave problem. And here you can see the mechanism by which it makes this transition. It makes this transition by these space-time dislocations. Again, this is angle and time going vertically. And you can see that you get different space-time dislocations which take you somewhere into the region of stable states. And in this particular case, you're losing 6 different rolls or roll pairs, and you're going from 31 to 25. So you don't really know where you're going to wind up. That's a complicated process. But we went through a lot of those details. Yeah, this is just showing this space-time dislocation. And Edgar showed an example of this. And you can actually do some very nice comparisons between a complex Ginzburg-Landau equation and all the properties in here, but I'm not going to talk about that. So During the time we were working on this, my postdoc Ning Li made an interesting discovery, and that was, so this is circa 1994, actually maybe a little bit earlier. We were trying to break this azimuthal symmetry, so we put in a barrier here, and as Edgar said, I gave a talk at Berkeley in which I showed a nice movie, which sadly has disappeared in the buried disk drives of my past. In any event, it goes around these various barriers. And so Ning said, oh, if it goes around that barrier, what happens if we put a whole bunch of different objects in? And in fact, we had this wonderful movie where the little wave is propagating around triangles. It's going through a little tank track. And if there's an inner thing where the curvature is outward with respect to the normal vector, it actually propagates in the opposite direction. So if you have an inner cylinder and an outer cylinder, then this is retrograde and this is prograde on that surface, and then it runs around. But the other nice thing that we did is Edgar had pointed out, and we knew this from the work of Herman and Busa, is that you could kill that conducting boundaries have a higher transitional Rayleigh number. And so we just tried, we put in aluminum tape, and sure enough, that breaks this azimuthal symmetry, and now you can track out what the selected preferred wave number is in the middle of the band rather than having discrete values. So this was a nice demonstration that you could locally suppress that and break that azimuthal symmetry. And I wonder whether that might be a useful technique in some of these experiments to see if it made any difference. So.
Does the speed of precession depend upon, if you put in this barrier,
Yeah.
does it change the speed of the
No.
No?
Well, so that's an interesting question that it's an interesting question that I don't think anybody has studied in great detail. Ostensibly, to zeroth order, no, it doesn't matter. It just kind of goes around. You might expect that in areas of high curvature, there might be a local effect where it slows down a little bit or then speeds up along the wall. But those effects are very small, and nobody's measured them in any detail. Most people haven't appreciated this kind of geometry independence of this wall mode precession. So that was about 2000. I thought, well, we've done everything we can on wall modes. Wall modes are a thing of the past. And then in 2014, I was in at UCLA, and he was showing me water data of heat transport. And I said naively, well, but you have to include the contribution of the wall modes. And John said, we don't have any damn wall modes. And I said, well, I wonder why. Maybe at the higher rotation, he was in a bigger tank, so it was smaller Ekman. Maybe something happens to the wall modes, and they're somehow suppressed, and it really doesn't matter. So, I went away to do other things. And then in 2018, I was in Göttingen, and they had these interesting results, and Olga Shishkina and Zhuan Zhang were starting to do DNS to try to understand this, and wall modes reared their head again. So we looked at this, and as Rudy pointed out earlier, what Dennis Van Gil saw in the experiments, it's a beautiful experiment. It's taller than me. It's in SF6 at very high pressure inside a big tank. Gunter Allers and the people at the Max Planck Institute did this wonderful job on accurate measurements of heat transport with all sorts of sensors everywhere. But they couldn't figure out why there was this bimodal distribution. And it caused them not to publish many of their very nice results because they couldn't understand this. But Olga's simulations, it just pops out right out at you that there is in the turbulent regime, so these are done at constant Rayleigh number, which is the way the Max Planck guys like to do it. And in the temperature and the velocity field, you can see these stripe-like regions. And I have to admit something, and that is, John had convinced me that wall modes were unimportant. So when I looked at this, despite the fact that they look exactly like wall modes, the fact that they just shouted out wall modes, I decided that they might not be, and so I coined this term that this was a boundary zonal flow. And it was only at an APS talk when I was saying that everybody goes, "Aren't those wall modes? Aren't those wall modes?" I'm like, yeah, they're probably wall modes. Anyway, the reason that they're bimodal is because this is an m equals 1 mode. So, and this is in an aspect ratio of half. If you get small enough aspect ratio, the only thing that can fit is an m equals 1 mode. And so we did some simulations, as a function of the radius. You see nothing in the middle, and then you see, as a function, you see how the bimodal distribution separates so that you get bigger differences as you go near the wall. And this is the experiments that were done in the SF6. And so the whole thing kind of works nicely. And one of the kind of amazing things is that the transition between a unimodal and bimodal distribution is almost exactly at this transition between what is called the large-scale circulation and of the buoyancy-dominated regime and the rotation regime. So as soon as you kind of get any kind of rotation effect, the wall modes seem to appear. So about the same time, Rudy's group did numerical simulations and got very much the same thing. Here is vertical velocity contours at a lower Rayleigh number. This is at Ekman 10 to the minus 7 and a higher Rayleigh number. And you can see that even in the turbulent state where the bulk mode has come in, you get this coexistence of the wall mode state. And to be clear now, I call the boundary zonal flow the structure of the wall mode once it's interacting strongly with the bulk mode. So I think there is a differentiation. One of the things that was clear from the simulations that Edgar Knobloch and, well, Favier did the simulations, and Edgar provided the theory, I once gave him a hard time about, I did all this work and you came in and used a symmetry argument to explain all my data, and it seemed like a cheap shot to me. But, in theory, one good idea is worth a heck of a lot. So I had to give it to him. In any event, that's what he said the other day, I did all this and didn't have to do any work. One of the things you'll notice right away, so these are simulations that Favier did at 10 to the minus 6 and an aspect ratio of 3/2. More modes because wider aspect ratio. Notice how thin the region of the localization of the wall mode is in UZ compared to its breadth in temperature. And that's important, and we understand why that is now. And they also observed this jet instability. Rudy also saw that the wall mode, as it became more nonlinear, produced lateral jets into the flow, which I'll show you more about. And this is a very nice paper that really connected directly for the first time the connection between wall modes and the BZF, because they worked at constant Ekman number and they went through the pure wall mode state into the bulk state and could show that they smoothly went from one state to the other. That was the right way to do that problem. And in fact, we learned from that. So we looked in more detail then at the different states that could exist, you know, again, at constant Rayleigh number, I think 10 to the 9. And again, we changed gamma, and you can see that it goes from an m equals 1 state to 2 to 4. And by that time, we were well on our way to understanding that wall modes were important. This is kind of a nice result by combining different Prandtl numbers, different aspect ratios, and different Ekman numbers and different Rayleigh numbers. We were able to get a pretty nice representation of how the frequency, whether you scale from omega or the older thermal dissipation time, that you get this pretty nice collapse of scalings for this quantity. I'm not sure there's any prediction about that, although maybe you guys there's a new paper in which Jeff and his collaborators Jeff Vassal has done an asymptotic theory of wall modes, and I wonder if something like this comes out of that. Yes?
So just kind of along those lines, I think that in that case we have like a reduced Rayleigh number, which is Rayleigh times Ekman.
Yeah.
So if you fix the reduced Rayleigh number and take Ekman to 0, then
that'd be Ekman 1/3, Ekman 4/3. So maybe that's where the Ekman to the 1/3 comes in.
But
right?
for us, we have a finite precession velocity at 0, or in the limit of 0 Ekman number at fixed Ekman times Rayleigh. So I think that's inconsistent with what we're seeing.
Okay. Okay.
Maybe. I mean, just looking at it quickly.
Interesting Keith story in the middle of the of this. I remember. So whenever I would go to Boulder, we would go to Lucille's, which is this Cajun Creole breakfast place that Keith loved to go to. And I remember showing him the first results of our wall mode contours, and he said, "You know, Jeff tried to make asymptotic theory, and he always kept running into these singularities in the contours." And his code always kept blowing up, and he couldn't do this. And then he saw my thing and said, "I'm going to have to get Jeff to go back and do this again." So I think he revisited that because Keith saw our results and pinged Jeff to work on that paper.
Yeah, and then Jeff pinged us.
Yeah.
And then it got.
These guys are the computational brains and motivation behind that paper. So thanks very much. It's a beautiful paper. It's available on the archive. Okay, so by the time we had done stuff, so these are all the experiments that Stefan Weiss did with Marcus Vetti at the Max Planck Institute in the SF6 and compressed gases. These are the contours that we did at constant Rayleigh number. Here I've normalized everything by the wall mode onset, so Rayleigh critical is here, and these are constant Rayleigh number in that plane. And it was very clear that we needed to reproduce what Edgar had done along constant Ekman number to understand what was going on. So I'll get to it, but one of the things that you see, which is kind of counterintuitive, is that the heat transport, well, it's peaked near the wall, you get that, but it's actually negative at kind of this value. And that always confused me. Why is the heat transport actually locally negative? And what does that mean? It means that upwelling is taking cold up, and downwelling is taking hot down, which seems wrong. So it always worried me, but there's a good explanation for it. So we did comparisons between different mode number selections of wall modes and what we call the BZF in various conditions, and they were all totally consistent with what you would expect from wall mode states. Now, the key paper here in terms of understanding what's going on in wall modes is this 1993 paper, which, despite Edgar's notion that it was inspired by his work on finite cylinder modes, it was actually inspired by our work, which preceded his by several years. So, you know, it's funny how we look back on things, and I may be wrong. I have never actually asked Herr Professor Busa where he got the motivation, but I'm pretty sure it was from our paper. But that's ancient history. So here's what happens. So there's a number of things that there are a number of things that are true.
Bob, do you want to talk more about that?
You think I'm a bitter old man.
We're all friendly here.
I was hoping Edgar would be here, but he knew I was giving a talk, so he left early. Sorry, Edgar. I hope you're not watching this.
He's on YouTube right now. Watch it.
He's over that age.
Edgar and I go a long ways back. I'm sure he'll only
survive.
take moderate offense. So one of the things that is confusing is where the onset is for these different modes. And in order to understand that, and I'm hoping you guys have large amplitude, like Mike was talking about, there are these asymptotic scalings for the marginal stability boundary at large deviations in k. It goes like k squared and k to the minus 4, or which one was that, Mike? You know, asymptotically large k, it's k squared and k to the minus 2.
It's like Ekman to the minus 1/3. Is that what you're...
No. So if you look at the marginal stability,
Oh, the shape of
the
the
shape of the
marginal
marginal
curve.
stability. It's like, it's a little curvature at the bottom, but it's scaling one way with k and the other
K to
way
the
with
minus
k.
2 and K to the 4.
And yeah,
Yep.
would actually be useful because, as I'll show you, if you go to very small cylinders, what happens is the onset of heat transport gets reduced by almost a factor of 2. So, here's some plots of what you expect for different onsets, and it's counterintuitive, 5, 6, 7 mode numbers at aspect ratio 2, but you can get it flip-flopping back and forth because it's all with respect to what the infinite system wave number is and how that particular mode number falls with respect to that can vary. Okay. Now, this is quite amazing, and I have no idea why this works. But if you look at Hermann and Busa, he computes eigenfunctions for the different quantities, the U's, the temperature field. And one of the things you notice is the eigenfunction of velocity has this Ekman to the 1/3 scaling on it. The temperature does not. So as Ekman changes, the ratio between the decay of temperature and the localization of velocity changes a lot. It's only weakly dependent on Ekman through the critical wave number dependence, which is slow. And so, kind of coincidentally, at an Ekman number of 10 to the minus 4, which is what we were working at earlier, they're about the same. But when you go to an Ekman of 10 to the minus 6, which is where we're looking at, and it gets worse as Ekman goes down, this separation now becomes large, and the velocity boundary layer gets thin, whereas the temperature field is extended.
Does that
Could you
have
go back to
Prandtl
that?
number dependence?
Yeah, that's what I was gonna. Can you go?
It is weakly Prandtl number dependent. So the Busa, it's also weakly Ekman number dependent. So you can go to Busa's figure 3 and he has the eigenfunctions. He's usually talking about either Prandtl number 7 or Prandtl number 1. All the figures don't include all of those things, but generally these things are pretty robust to Prandtl number changes, provided you don't get too low. It's either 1 or 7 is the conditions that he looked at.
And is there a implicit H in there somewhere? What happens with H? If you go to a taller cylinder, do these change in any way?
This is all the distance from the wall in H units. Okay, so this should be X over D, and this is a flat wall, right? So this is curvature doesn't matter, infinitely extended wall. Do I get traveling waves or not? And you do, and these are the eigenfunctions associated with that. If you look at if you look very close to onset, so this curve here, the onset is something like 2.9 or 2.8 times 10 to the 7th, so you're just a little bit above onset. You get this curve, and if you compute the eigenfunctions of velocity, and so uz, u phi, and u sub r, so u sub r is the radial velocity, the azimuthal velocity u phi, and the vertical velocity, you can see that the match between our simulations, very close to onset, and the eigenfunctions of Hermann and Busse are almost identical. You can't see the difference. It's this tiny difference between dotted and dashed, except for u sub r. And I think that is really the only contribution of the wall curvature close to onset is this small deviation of u sub r. And you also notice that whereas these things wiggle and go negative, this guy is always positive. And the maximum peak of that is almost identical to the zero crossings of those guys. So now, what happens to the temperature? Well, the temperature does just what it said. It slowly varies. It's got to be asymptotically flat here to satisfy the insulating boundary conditions. And then it's basically, this is close to onset, and maybe there's a little bit of exponential decay. This is the radius. But by and large, it's just flat. So this explains why the heat transport is negative. The velocity in u sub z has this wiggle in it. It's going up, and then it's going down. The temperature is varying very slowly, so it advects whatever that temperature is. And if you just take, the Nusselt number is the average of the correlation between u sub z and t, but if you just take the average of these, you don't take their correlation, you just take the average values, you almost directly reproduce the heat transport. So that explained that conundrum that I didn't understand. Now these are the profiles. So if you go to the peak of that distribution, now I'll get to that in a minute. Actually, let me go back. These are the distributions from 3 times 10 to the 7th up to 3 times 10 to the 8th. That's a Rayleigh over the wall thing of 10. Over that entire range, you can scale these onto one curve, and they fit almost exactly to the Busse eigenfunction. For who knows why? I mean, you expect the eigenfunction only to be good in the linear limit of small amplitude, but it works over a range of Rayleigh over Rayleigh wall of 10. It's actually quite amazing. So anyway, these are so if I go to the peak of that distribution and I look at the angular change, right? So in movies, these things go by. But you can see that by the time you get, this is a kind of weakly nonlinear one, it's barely changed from a sinusoid. It starts to develop these different shapes. Eventually, it has these cusp-like features. And when I come back to conducting wall modes, I'll talk about this a little bit more. but you get this huge deviation, hot stuff going up there, cold stuff going down there. It's very asymmetric. And by the time you get, this is just about the onset of the bulk state, you get these striations that you see that permeate the wall region. Okay. Now, so this was previously seen. We saw it as well. You get this jet instability. See if I can play that again. The wall becomes unstable. You get these jets that squirt in from the boundaries between the two upflow and downflow regions and meet in the middle. And this starts right about here. And we went back and forth. We did some transient measurements of the heat transport, and what you could show is that the static wall state had kind of this kind of heat transport, and the additional contribution, which is subcritical, was being contributed by this jet instability. And here's what it looks like later on. You can see the lateral jets.
You get the jets only in the only when the modes are processing, right?
Well, they're always processing. What do you mean? Well, so that's one feature of it, is that the wall modes undergo this instability and send jets out into the middle, which then, so even before the bulk instability comes in, you've got stuff going on in the middle. So you might expect that that would distort the linear stability in that region because you already have action happening. The other thing that you see is that the wall modes are affected by the bulk state in some way. Because again, you've got finite amplitude at the walls. Do those act as nucleation centers for the bulk instability near the wall? And what you see is these oscillations that come and go. Here you go. And these things have about twice the bulk linear scale, which has led us to conclude that what's happening is these are signatures of bulk instability coming in. You see the strong inflow-outflow associated with the jet instability, and I have to admit again to an embarrassment. When we early on did some averaging, we made the unfortunate choice of being at the midplane, which is the place where things reverse. As a consequence, we got a wrong scaling, and rather than the length scale of that region going like Ekman to the 1/3, it went like Ekman to the 2/3. And Keith always said, "What is going on there?" Well, we just messed up. If you go up here where you get strong circulation, then it's because you're getting first order cancellation, and it's the next higher order term, which is Ekman to the 2/3. So mea culpa. Okay, so in fact, if you look at the length scales derived from going to the rotating, 5 minutes, perfect. If you go to the rotating frame, you can look at the zero crossings and the maximum of U sub r, and they're remarkably insensitive to the Rayleigh number in the wall mode state, and they only really start to change when you get into the bulk state, in which they start to spread out. There's some scatter here, but that has to do with the influence of the jet instability. Okay, now the bad news. Well, the bad news is you can't just do a bulk wall mode separation in any clean way. It really depends on how you do that separation. The total are these black these black curves. Here is the non-hydrostatic QG asymptotic prediction, and depending on how you subtract, where you put that radius, you get different answers, which is kind of annoying. Although the dependence over this rather limited range looks pretty close to linear, regardless of how you separate it. I would just like to point out that you can see prograde precession, even though it looks like this is backwards. It's because it's a different sign of rotation. This is work that Susanna did in her 2017 paper. Small aspect ratio, rather small. We also see something that settles into a prograde, and I put this in terms of a Hove-Muller plot, which I had no idea what it was until somebody said, oh, that's just a space-time plot. Okay, so prograde things can exist for certain values. All right, in the last couple minutes, I'd just like to talk about conducting wall modes. One of the things that happens is for conducting wall modes, the scaling of the onset is the same as for bulk. The other properties have different scaling, so you can differentiate them, but this has a coefficient about half of this value. When I told Keith that, he said, what? I didn't know that. And that was one of the few times I told him something he didn't know. Usually it was a much more one-sided conversation. And so this is what, one of the interesting things that happens is that when you put conducting wall modes, this differentiation between the temperature field and the velocity field vanishes, and now they're both localized, having to do with, in this case, a zero boundary condition for theta at the wall compared to a d theta dr condition for insulating boundaries. And you can see there's some interesting properties here, which we haven't really characterized in any great detail. But the heat transport, so here's the heat transport in the insulating case. It kind of goes up slowly, it saturates to some degree, and then it takes off again when the bulk state comes in. Conducting boundaries suppresses that a lot, and then it increases really rapidly so that, and I have no idea if this is a coincidence or not, at the onset of the bulk state, they're almost identical heat transports. No idea why that's true or if it has any generality. But interestingly, in the conducting case, the heat transport is actually greater in the conducting boundary case than it is in the insulating case. Very counterintuitive to me. Okay, yeah. So we've measured some things. So I just wanted to show this. Here's, again, at the peak of the vertical velocity profile. You remember how in the insulating case I was getting order h variations in lateral variations. The constant boundary, constant temperature boundary conditions suppresses that a lot so that the oscillations are much slower. But this has a definite periodicity, again, associated with the bulk onset periodicity. So I'll just finish with that. There's a lot more we can do on conducting boundaries. And let me just say that conducting boundaries are actually rather relevant to these compressed gas experiments. They're done in containers where the conductivity of the walls is much higher than the conductivity of the gas. And so at least for onset, it's very likely that in those systems, the conducting boundary solution is a better description. I'd like to thank all my collaborators over the years, Fong Zhang and Victor Steinberg. Victor Steinberg introduced me to this problem many years ago. Edgar for his theoretical insights. My postdoc, Ning Li, who stopped doing hydrodynamics and went off and started a company building modular nuclear reactors. He's definitely my most successful student in terms of the valuation of his company. Yuanming Liu, who did a lot of the work on that I've talked about, the earlier work. Juan and Olga at the Max Planck Institute have been wonderful to work with. And all the people that I've had numerous conversations with over the years. John, Rudy's, Susanna, Jeff Vassell, who I knew as a graduate student with Keith, and of course Keith. And thanks IPAM for sponsoring this great workshop. It's been lots of fun. Thank you.